So let's start off Unit 2 with a little bit of background knowledge. In order to fully understand what's going on in different biological systems, we have to understand some of the things that biological systems are bound by, some of those rules. One of those things that biological systems are bound by is chemistry. So we're not going to get super deep into chemistry, but we do want to remind ourselves of some things or learn about some things if we've never learned about them before to give ourselves the background knowledge required. So for this topic, we're going to be talking about biological chemistry. And you can see the readings there if you're trying to follow along with the textbook. So why do we care about biological chemistry, or biochem as it's also known as? It's because, again, all living things are made up of chemical components, and it's those components that determine their function. This is going to help us lead into the next topic, but first let's give ourselves an overview of the basic chemistry that biological systems depend on in order to function correctly. So when you hear the word chemical, what's your first thought? It's probably something in a chemistry lab, some sort of mystery liquid or something along those lines. But in reality, chemicals are everything, right? Water would technically be a chemical. Right? Everything that we see, everything that's ever been has been made of atoms. And thus, because it's made of atoms, they are chemicals. Right? So the word chemical, when used casually, we're kind of talking about something that might cause some sort of reaction that we can see or has a certain smell or look or appearance. But in reality, everything is a chemical. Some of these atoms are classified together because they share properties. We call that an element. So the element is the substance that cannot be broken down into any other substance, and they have their own particular properties that make each element unique and different from the rest. An atom is a single unit that cannot be subdivided further without losing its properties as well. Right? So one atom would be an element. An element, you could have many atoms of the same structure, the same kind of makeup, with the same properties. So an atom is a basic unit of matter, which is basically what makes up everything that ever exists in the universe. So here's some examples: sulfur and fluorine, gold, bismuth, mercury, iodine, carbon, and uranium. Now let's look at the anatomy of an atom, so to speak. Let's look at the parts that make up an atom. The center of the atom is called the nucleus, right? And there's going to be a few components that hang out in the nucleus, but not every part of an atom is found in this nucleus. The parts that we're talking about we call subatomic particles, of which there are 3 different types: protons, neutrons, and electrons. Let's look at the proton first with a charge of +1. It has a +1 charge. The neutron does not have a charge. It's neutral, hence the name. And the electron has a negative charge. So we have protons with a positive charge, neutrons with no charge, and electrons with a negative charge, which if you have one of each of these, that gives you net 0, right? The neutron doesn't do anything, and the proton and electron charges cancel out. We find the proton inside the nucleus, as well as the neutron, but the electron does not hang out in the nucleus. The electron is found in this electron cloud around the nucleus. And so it's kind of free-floating and moving around within this cloud surrounding the nucleus. In terms of size, the protons and neutrons are about the same size. They're about equal, but the electrons are super, super, super tiny. It's so small that their mass, their weight, is considered negligible. So let's look at this all put together. So if we look at the basic structure, here we're looking at a hydrogen atom and a carbon atom. So we're looking at 2 different atoms from 2 different elements. For the hydrogen, we see we have a proton here in the nucleus, an electron in the cloud, but there's no neutron. So this is as simple as it gets. This is as simple as we can possibly get when looking at the different elements. The carbon atom's a little bit more complicated. Here we have 6 protons, 6 neutrons, and they're making up the nucleus, and then 6 electrons free floating in this cloud around our nucleus. But we notice that this cloud kind of has different layers. We have an inner layer and an outer layer. We'll talk a little bit about that in a little bit. So when we're looking at these, we'd want to not just be familiar with what an atom is and the basic structure, but also what are the different elements and how do we organize them and what information can we get from them. So the atomic mass is the mass of all the protons and the neutrons in an atom. Remember I said that the electron is so teeny tiny that its weight is basically, or its mass I should say, is basically negligible. So we don't really count that so much. And the periodic table is going to have useful information, like atomic mass, about all of the known elements. So let's kind of break down our periodic table if we're looking at one element from the table and kind of discuss what some of these different numbers are. We have the atomic number, which is right here. This is the number of protons that we find in the nucleus. And what you'll notice is that the proton number is going to define what element we're looking at. So something like oxygen is always going to be 8. Always 8 protons. The element symbol is the abbreviation, so something like H for hydrogen, O for oxygen, so on and so forth. The full name of the element, and then the atomic weight. The atomic weight, it looks a little weird because it's 15.9994. Like, why do we have this weird decimal? Because this number is an average mass. It's an average mass of all the isotopes. We'll talk a little bit about what isotopes are. But we're basically looking at what's the average mass of all the different oxygens that are out there. And then for color coding, the following these colors are used for the book. This is not something that's necessarily on a periodic table, but these are some of the really common elements that we find in living organisms, and this is how your book will color code them. White for hydrogen, gray, black for carbon, light blue for nitrogen, orange for oxygen, blue for sodium, like a darker blue, yellow for phosphorus, this kind of marigold, dark yellow, light orange for sulfur, light green for chlorine, pink for potassium, and green for calcium. But again, that's something that's going to be used through the book. It's not necessarily something that is used on every periodic table. So here we see the periodic table in its entirety. So if we notice again, we have some color categorization going on, and we're categorizing them based off of the types of elements they are. And these are all these ones that are coded together have similarities. They're not the same element, but they have similarities in how they react and what they do. So like all the alkali metals, alkaline earth metals, right? We have transition metals, and then down here, coming from this location here, we have the lanthanides and the actinides, post-transition metals, metalloids, other nonmetals, halogens, and then the noble gases. So all of these color-coded areas, they have things in common. There's some similarities between the elements of the same color there. But you're probably wondering, why is the table split like that? I mean, look at this. Why not put them in nice, neat rows all the way across? And why the heck do we have these 2 rows removed from this area here and placed down below? That doesn't seem to make sense. Because if we put it all out, right, we'd had to put those rows in, we would have to split it like this, and it wouldn't really fit. So the lanthanides and the actinides, they're often really big. They're usually very unstable, and we don't really use them for much in general chemistry, so we just kind of cut them out and put them down below and say, hey, if you want to see these guys, look here. And then you can look down below. But these are things that are not typically found in large amounts. These are things that typically don't hang around for very long because they're super unstable. So they don't really last very long, and we don't really see them used in any sort of regular chemistry process. So like I mentioned before, all of those different elements, they had that number in the corner, like oxygen had 8, and that was telling us the number of protons. The protons determine which element the atom is. So proton number is not going to change from one atom to the next in the same element. If you change the protons, you change the element. Right? And again, we call that the atomic number. It's kind of giving us a number, like a name tag. That's one of those first pieces of information we can get about this element that we're looking at. So let's look at a couple examples. We have carbon that has 6 protons, gold has 79, uranium 92, mercury 80, iodine 53, hydrogen just 1. So all of these elements, their atomic numbers are the numbers you see there. Carbon has 6 protons, so its atomic number is 6. However, I did say that the atomic mass had to do with isotopes, and isotopes are members of the same element that have different numbers of neutrons. Remember, the neutron is a neutral subatomic particle. There's no charge to it. And so we can vary there a little bit. And when we vary with the number of neutrons, we call that an isotope. So it's going to change the mass, but it's not going to change the atomic number. Because remember, the atomic number is associated with the proton, not with the neutrons. So to calculate the number of neutrons in an isotope, subtract the atomic number from the atomic weight, since the atomic number always represents our number of protons. So if we look at iron 56, the atomic mass is 56, 26 protons, we have 30 neutrons. Right, so you can have more neutrons than you have protons, and it's not going to really change much except making it a different isotope. Iodine 131 has an atomic mass of 131 minus the 53 protons, giving us 78 neutrons. So it's a big difference there. So let's look at carbon as another example of our isotopes, where, again, same number of protons. We see it across the line, 6, 6, and a 6 here for all these different isotopes of carbon. But the difference is the neutrons right here. For carbon 12, we have 6. For carbon 13, 7 neutrons. Carbon 14, 8 neutrons. And so our atomic mass is different, and that's where these numbers 12, 13, and 14 are coming from. So carbon 12, that's just standard carbon, where we have 6 protons, 6 neutrons, and 6 electrons with an atomic mass of 12. That's what we would expect just thinking about carbon and the basic setup of an atom. But over here with carbon 13, the atomic mass is different because we've added in a neutron. And same thing with carbon 14. The atomic mass is different because we've added in 2 neutrons. So not every isotope is stable though. Some of them are unstable, and we call those radioactive isotopes. So because they have this difference in protons and neutrons, sometimes that can cause the atom to lose its stability and break down spontaneously, and that releases different types of energy. So we can shoot off something like a proton or an electron. Sometimes this can be harmful and others are not harmful. We do utilize this in our regular lives. Radioactivity is useful for things like trying to figure out how old a fossil is, because we know how the rate, what the rate is of decay. So these radioactive isotopes, even though they're unstable and they break down spontaneously, there is a pattern. There's a regular interval that they kind of break down at. So we can use that and know what the rate of decay is, right? We can use that information to figure out how old something is based on the ratio of the different isotopes. We also use radioactivity for things like medical imaging. So if you have to get certain images like a PET scan done, that would use something that's radioactive. Certain treatments, like if you have problems with your thyroid, you may have to take radioactive iodine, since if you need to kill off part of the thyroid, since if it's overactive. So there's a lot of uses for radioactive substances. It's not all bad. Right, moving on, there's about 25 elements that we find within the human body. So, looking at that whole periodic table, we don't see everything in the human body or in living things. Like those lanthanides and the actinides, we're not going to see those in the human body. And most of the human body, most of what makes you you, 96% of it comes from 4 elements: nitrogen, oxygen, carbon, and hydrogen. 96%. That's a huge percentage of just 4 elements that make you up. And it's the different combinations and different ways that these are bound together that gives us all the variety of the different chemicals that make up our body and the different molecules that make up our body. So here we see the breakdown with the percentages, because the previous list was in no particular order. So the big 4, oxygen makes up most of us, 65%, with carbon being a good 18 or so percent, hydrogen, and then nitrogen. And the remaining 4% is things like calcium, sulfur, phosphorus, sodium, potassium, and chlorine. Trace amounts, meaning less than 0.1% of 15 other elements, are also found in the body. So there are other things like iron. We do find iron in the body, but not very often, very, very rarely. So it's an interesting way to look at this and kind of know like what makes up you. This is the general breakdown, right, of the different elements that are found in your body and all the people that you know.